Hello everyone, and welcome to today's webinar, Unlocking the Power of Spherical Indexing with EDAX OIM Matrix. Before we get started, I'd like to cover a few housekeeping items. If you have a question, please submit it through the questions pane on your console. Any issues regarding connectivity and webinar viewing will be addressed immediately. We will attempt to answer any questions for the speaker at the end of the presentation. If we do not get to your question, we will follow up via email after the webinar. Now I'd like to introduce the speaker for today's webinar. Dr. Johan Westrat completed his PhD in physics at the Nelson Mandela University in South Africa in 2011. He's currently working as a research associate at the Center for Electron Microscopy and Analysis at The Ohio State University, specializing in SEM-based characterization techniques. His research focuses on the relationships between structure and properties in structural materials, specifically ultra-hard ceramics, high-temperature steels, and titanium alloys. Johan's work includes developing and applying novel correlative quantitative microstructural characterization techniques. These techniques are combined with machine learning to predict the mechanical properties of these materials. He primarily uses high-resolution SEM-based techniques such as TKD, EBSD, and ECCI, combined with simulation software to extract phase, orientation, and dislocation information at a nanometer scale. Now over to you.
Thanks for the introduction, Jonathan. So in this presentation, I'll provide some practical examples of how spherical indexing can improve your EBSD analysis. And the first area of analysis is looking at deformation in materials. And with the traditional Hough-based indexing, you get a lot of noise when you look at the misorientation analysis. But with spherical indexing, that really clears up the orientation maps by having a much better angular resolution. So the next area where spherical indexing really helps is when you have crystallographic similar phases, and in some cases Hough-based indexing algorithm can misidentify the phase, and with using spherical indexing you get a much clearer phase mapping. Then a lot of my research involves quantitative analysis for very small phases, much less than 100 nanometers. So with spherical indexing, it's much better at distinguishing the orientation and the phase from patterns that have some overlap. So that really improves the effective spatial resolution that you can get from your EBSD analysis. And then lastly, the research involves using multimodal SEM techniques where we combine EBSD with chemical information, EDS, and also the transmission SEM detectors in the SEM to then quantitatively analyze the microstructure. And I'll show you how OIM Matrix can analyze and integrate it into one program where you don't have to use separate programs to do these kinds of correlative analysis. As an outline of the talk, we will compare Hough-based dictionary and spherical indexing algorithms, discussing their strengths and weaknesses. And then I'll just cover some of the additional tools that I've used in analyzing a list of practical examples, including a single crystal silicon, deformed stainless steel sample, polycrystalline diamond, dissimilar welds, and then fine structured alloys that we use to then map out the orientation, the phase, and then also identify the secondary phases in these high temperature steels using the different SEM modalities. But just before that, I just want to tell you about the SEM course that we are having at CMAS. And this course is really comprehensive, where it covers all the areas of SEM analysis, from sample preparation, the microscope hardware, how to best acquire the data, and then also in-depth discussions on analyzing EBSD and EDS data. These talks are all given by experts in the field from industry and academia. It's a set of lectures that run asynchronously, So you watch them online and you can discuss in the forums and ask questions. And then the second component, there's a 2-day workshop where you work personally on the microscopes, hands-on, applying these techniques on different sets of samples. The other component, if you can't make it in person, you can sign up for the manager track, where we will analyze the samples for you on your particular material, and you can do that remotely as well. So if you don't have the time to travel to CMAS, you can watch the lectures, learn all the materials, and then the practical component, we will then perform microscopy on your particular sample. So if you want more information, you can just follow the QR code on the screen. So Hough-based indexing is sort of the standard indexing algorithm that's used in EBSD analysis. And for electron backscatter diffraction, we take the sample, we tilt it at 70 degrees. That's to maximize the backscatter or the signal that come out of the sample. And then we have a detector that will then detect these backscattered electrons. Now, for a amorphous sample with no crystallographic ordering, this background of the backscatters will all just be sort of a diffuse background. But for a crystalline sample, we get additional diffractional effects from the crystallographic planes, and it forms these Kikuchi bands. And each one of these Kikuchi bands are related to the crystallographic plane inside of the sample. And then to determine the orientation, you transform this Kikuchi band sample into Hough space. And so instead of having to find the position of the line, you just have to find the position of a point. Now you've determined the position of and the angle of these lines, and then using 3 sets of lines, you can then calculate the angles between those lines. And from those angles, you can then compare that against a pre-computed table of angles for the candidate phases that you provide for the analysis. And that's how it then look for the best match for the phase. And then looking at the low index zone axis, it can then use that to determine the orientation of the crystal at a particular point. And then it scans the beam across the sample surface and determine the orientation for each point. Now, typically these patterns are not saved because they take up a lot of space on your hard drive. But if you want to do the spherical re-indexing or dictionary re-indexing, you have to save all these patterns. Now, this is sort of the standard analysis. It works quite well. You can map out the orientations and then do a misorientation analysis, and then also look at statistically analyze it for the texturing that you might have in the sample. Now, traditional Hough indexing works quite well for the most cases, but there are certain situations where Hough indexing really struggles. And the first case is when you have noisy patterns. So if you have these bands are not very clear, then the algorithm really struggles to find these lines to determine the orientation. And you can see that the resulting orientation map looks very, very noisy. The other area where it sometimes struggles, if you have 2 phases, for example, that will have exactly the same angle of bands in the position of these Kikuchi lines. So these 2 phases, the one is the body-centered iron, and then this M23C6 precipitate is a FCC structure, but they happen to have bands that are very, very similar. So if you only look at the position and the angles of the bands, you really struggle. So this grain here is actually the iron, but you can see that the colors are all mixed up between iron and this precipitate. You can also find that sometimes for a particular crystal, there might be multiple orientations where these bands overlap, and that's called pseudosymmetry. The other area where Hough indexing sometimes struggles is if you place the electron beam right at a grain boundary, and in that case, you will collect information from the interaction volume from 2 crystals that might be in a different orientation. So you have these bands that are overlapping, and then with the Hough-based that just looks at the number of lines, these other additional lines will then confuse the algorithm, and it will struggle to identify the orientation. And also, if you have very small precipitates, the interaction volume might be bigger than the actual size of the feature you're looking at, and therefore you collect information from the surrounding matrix as well, and then the algorithm will struggle. The way that you calculate the orientation from these bands also limits the angular precision. And the way that we measure the relative angular precision, we look at a particular pixel where we have the orientation, and then we look at the nearest neighbors next to it, and then calculate the average misorientations with all the neighbors, and that's called the kernel average misorientation. And here we see a single crystal silicon, and it should have all the same orientation, and there should be no misorientations between the different pixels. But if you look at the orientation spread here, there's roughly about, this color is green and the scale goes up to 1 degree. There's about half a degree misorientation from pixel to pixel. So the angular precision for the Hough indexing in this case limits that resolution. Now, there's a number of practical ways that you can improve the performance. So usually if people come and we see that the patterns are very noisy, that's related to the sample preparation. So you really need to make sure that you optimize your sample preparation. Then another way to increase the signal to noise is to increase either the beam current or the beam energy. And then lastly, you can then increase the scanning time for the pattern. So if you optimize your acquisition parameters, you can really make sure that you get the best possible patterns for your particular analysis. Pseudosymmetry and phase discrimination is a little bit more difficult to deal with, but you can use like the chemical information to help with the phase discrimination, and then also playing around with the reflectors, that can sometimes also help. In terms of overlapping patterns, to decrease the interaction volume, you can decrease the beam energy, or you can use a thin foil that will, so we use a different modality called transmission Kikuchi diffraction. And then lastly, for the angular resolution, found that it's quite sensitive to the pattern quality. So if you have better quality patterns, then that usually helps. Okay, so with the practical things that you can do experimentally to improve your analysis, you can also then change the algorithm. So I've explained the normal Hough-based indexing, and with Hough-based indexing, you're just using the position of the bands, and you're not taking the intensities of the pattern into account. Dictionary indexing and then also spherical indexing is what we call whole pattern methods, where we use most of the information inside of the pattern, including the position of the bands and the intensities as well, to then determine the orientation. And the way it does it for dictionary indexing is that you pre-compute a library of orientations, and you compare your experimental pattern to this pre-computed library of patterns that represents all the possible orientations, and then you find the best match in this library to your particular experimental pattern, and then it goes to the next pixel and it repeats that analysis. Now, the big trick is to really accurately simulate all these patterns, and that's no easy task. So to understand how those patterns are simulated, we need to just have a look at how the diffraction information is projected onto the EBSD detector screen. So here we have the electron beam coming in, and we have a crystal in a particular orientation, and then we have this diffraction information that can be represented by this Kikuchi sphere. This diffraction information then propagates out, and it will intercept, or it will be projected onto your two-dimensional EBSD detector. And that point, normal to the detector, to the position of the where the beam hits the crystal, that's called the pattern center, and that's quite an important parameter. So as you move your beam along the sample, and the crystal orientation changes, this Kikuchi sphere is connected to the crystal and it will rotate, and you'll get different projections onto the pattern. Now, in order to simulate, we need a model that will simulate the diffraction from this crystal. And the model that's used, it's explained in this paper here at the bottom, but essentially it takes two components. The first component, it performs a Monte Carlo simulation where it calculates the angles of the backscatter electrons and their associated energy. So as the electrons move through the sample, it will lose a certain amount of energy. So the Monte Carlo simulation calculates that energy losses and the angle at which these backscatter electrons will come from the sample. And then it solves the second component. It uses the Schrödinger equation to solve the Schrödinger equation in your particular crystal. So for a nickel, the pattern on the screen here displays the dynamical simulation for the Kikuchi bands for a nickel sample. And then you combine the backscatter electrons with the dynamical simulation to get your three-dimensional master pattern. This master pattern is usually projected onto a flat equal area projection. Now, to simulate the orientations, you would then sample all the orientations for your particular crystal. So this is an example of the cubic crystal. And for all the possible orientations, we space out these orientations by 1.4 degrees. And you'll take the 3 Euler angles. And then what the simulation does, it rotates this simulated master pattern to that angle and projects it onto the detector. So you would need you go from the master pattern, you use the detector parameters, meaning the distance and the number of pixels, and then you take the orientation information and then project that information onto a 2D pattern, which represents your simulated pattern. And then you go to all these points in orientation space to generate your dictionary that you would then compare to a particular experimental pattern. And then if you find, for example, this pattern corresponds the best to your experimental pattern, then you know that is the particular Euler angles for that particular point. Now, if you compare dictionary indexing to Hough indexing, it's especially performs quite well when you have very noisy patterns. So the dictionary indexing, or when you use the whole pattern method, it's really good at working with noisy patterns. So if you compare the Hough indexing, even after pattern averaging, you can see a lot of noise pixels, while with dictionary indexing, you still get quite reliable orientation information. The problem, however, with dictionary indexing is related to the sampling of the orientation space. So for a cubic crystal, if you space out these points by 1.4 degrees, you end up with over 300,000 points or patterns that you need to compare against your experimental pattern. And that can make the analysis quite slow. And then it gets worse if you analyze crystal structures with decreasing amounts of symmetry. So for an orthorhombic, the number, if we keep the angular spacing the same, you can see that the number of patterns increases by a factor of 6, and that will increase the time for analysis. Also, you're limited by angular resolution of 1.4 degrees. And if you want to improve the angular resolution and increase this number of points, you can see even for cubic symmetry that the number of patterns in your dictionary just explodes. So typically we would do the first part of the analysis using a discrete grid of 1.4 degrees, where we have a manageable amount of patterns. And then we determine for a particular point in your sample, we will then get to an orientation, say for example, that's the best matched pattern, but the true orientation of the material might sit somewhere here in this darker green region. So with dictionary indexing, there's usually a second step where we refine these orientations using an algorithm to iteratively refine the orientation. So using that initial indexing orientation as a starting point, it can then iteratively refine to find the true orientation. And that's called real space orientation refinement. Spherical harmonic indexing is actually fundamentally different to dictionary indexing, but in a way it's also similar, meaning that you're not only using the position of the Kikuchi bands to do the indexing, but you're using the whole pattern. Now, remember with dictionary indexing, we took the master pattern and then we simulated the pattern by projecting it onto a two-dimensional detector. In spherical indexing, we actually do the reverse. So we take the experimental pattern and then using that inverse projection equations, we project it onto a sphere. And now we have our experimental pattern on a sphere and we have our master pattern, and we can represent these intensities on a sphere by a spherical harmonic function. What we then do is we discretize the sphere into different orientations, and by rotating this master pattern, we can find the best match where the master pattern lines up with your experimental pattern. And by rotating this only one pattern and matching it to your experimental pattern, you eliminate the need to have this huge pre-computed dictionary indexing, and that really speeds up the analysis by quite a bit. Now, the details of this rotation and everything, it's described in the two papers below, and it takes the Fourier transform and then it performs a cross correlation, and then for these discrete points we can then work out how the master pattern must be rotated to match up best with our experimental pattern, and then we have determine the orientations. Now, a critical parameter is what's called the bandwidth, and that's essentially the number of, or the grid spacing, or the number of latitudes that we have in this grid. So as we increase the bandwidth, we can see that we have more and more details captured from, or more and more details from the experimental and the master pattern that we're matching it up with, and we'll get a better match. But that really increases the indexing time. So although it's not as time intensive as dictionary indexing because you're only comparing it against one pattern, it is quite sensitive to the this discretization. Now, just for comparison, in terms of the indexing speeds, the initial idea was presented by this group, and they implemented a software version that you can try it out. And then the group from Carnegie Mellon then used to exploits the crystal symmetries. So if you look at the master pattern, there's some symmetries here. And also, if you look at the Fourier functions, there's some properties of the functions where you can really reduce the number of computations. And what they've also done is to implement it to run on a GPU. And that implementation is then implemented in the OIM Matrix software. For comparison, all our experimental runs were done at a bandwidth of 127. And that's got a grid spacing of 1.4. And for this 60 by 60 pixel nickel pattern, it runs at 800 patterns per second on a laptop. Now, you might ask, okay, you have this discretized issue where you have fixed orientations. A nice property of the function that's used to rotate the sphere is that you can also do orientation refinement in Fourier space. And If you do this refinement with the spherical indexing, you don't necessarily need to do the real space refinement step afterwards. For all the experimental scans that I will show in this presentation, it was done at a bandwidth of 127, and we got indexing speeds ranging from about 400 to about 600 for the patterns that we analyzed. Additional tools in OIM analysis is called pattern averaging, and the simplest way to do pattern averaging to increase the signal to noise is just to look at the nearest neighbors, and you can just equally average these patterns out, and that would really improve the signal to noise. But then you're losing some spatial resolution. So they also implemented a non-local pattern averaging reconstruction algorithm. And instead of just averaging these pixels equally, if you look at, for example, this pixel here right on the grain boundary, it will weight the average according to the similarity. So only those patterns or orientations that are very similar to the pixel of interest will then be weighted favorably, and it will contribute more towards the average. And then those pixels from the adjacent grain, which is not very similar, won't contribute towards this average. And this really helps to increase the signal to noise, but also preserve the spatial resolution. And then the nice thing about the software as well, it sort of solves problems that you don't know you had. These analyses are re-indexing analysis are very sensitive to the pattern center optimization. So as you scan the beam across larger and larger fields of view, and if you move, for example, more than a pixel size, a pixel width of the detector, which is around 50 microns, the whole Kikuchi pattern will move, and that pattern center will move with it, and that can really influence the angular accuracy, and also sometimes, if it's really out, the phase analysis that you get. And there's a nice tools built into the OIM Matrix software that will allow you to not only optimize the pattern center, but also the shift of the pattern center as you scan across large fields of view. So into the practical examples. The first example, okay, before I get that, I just want to say that we used the microscopes at CMAS. We have a high resolution Apria microscope, and that has got a Hikari EDAX EBSD detector. And then on our Quattro instrument, we have a velocity high-speed EBSD camera that can scan to about 4,500 patterns per second. For practical use, most of the analysis here we get regularly scan at about 1,000 patterns per second with this detector. So the first example I use is a single crystal silicon, and the reason why I use the single crystal silicon is just to understand the sort of best case scenario. So for single crystal, all the orientations should be the same. And I scanned it at the parameters that we traditionally use for our analysis on most of the materials that we investigate. So we bin down the detector to 115 by 115 pixels, and then we used normal 20 kV, 3.2 nanoamps or 6.4 nanoamps. And in this case, we scanned it over a relatively large area with quite a big step size, and the sample was tilted at 70 degrees. So just straight out of the microscope with Hough indexing, if we do the kernel average misorientation, which is scaled from 0 to 1 degree, we can see that here at about 0, we get sort of an angular precision around 0.5. And then if you were to average these patterns, you can see that the angular precision improves quite a bit, but you have to be a little bit careful when you do the averaging of the patterns, because you're taking into account neighboring patterns information. And then when you look at the misorientations relative to its near neighbor, which is already captured by a particular pixel, you can smooth out the angular precision artificially by the averaging. So by increasing the averaging of the patterns, you can increase the signal to noise, but you just need to be very careful to do misorientation analysis with pattern averaging, because you're basically smearing out the orientation information. Now with spherical indexing without pattern averaging, you can see that the angular precision is much better. And if we stretch the scale from not going from 0 to 1, but 0 to 0.1, you can see that the angular precision is around 0.5. If we plot the histogram of these misorientations, we can see with just traditional Hough indexing, we get a spread between 0.6 and 0.2. If we average the patterns, that really improves the angular precision, but then with spherical indexing, it's just completely different angular precision. Now, how do we use this? So the first example is from a study that we got material from the University of Gatan. And in this case, we looked at a deformed 316 stainless steel sample. And in the deformed state, we have it in as extruded bar, and that's got a very high dislocation density. That goes into a furnace and you anneal out all the dislocation. So the annealed sample should have very low dislocation density. And then we conducted fatigue testing at different levels, and we interested in getting different techniques that could map out the deformation in this particular material. So with Hough-based indexing, if we look at the kernel average misorientation map, we can see that there are a lot of noise pixels from the Hough indexing. If we look at the kernel average orientation map, and then even in the annealed sample where we wouldn't expect to see a lot of misorientations because of the recrystallized grains, we can still see some misorientations, and that's due to the angular resolution limits of the Hough-based index. When we apply spherical indexing, no averaging, we can see that the noise pixels completely disappear. And now you can actually make out the slip traces and the low angle grain boundaries that formed in this deformed sample quite clearly. And then for the annealed sample, we can see that the misorientations completely disappear. So this is really important if you want to do dislocation analysis using EBSD, is to really improve. There are other methods. Usually people apply smoothing functions to really improve it, but in this case, it's much better to index the real patterns to determine the true orientations, and then do as little as possible of the smoothing functions that will artificially improve the EBSD analysis. If we change the color scale, this is sometimes a little bit easier to see. We can see these nice slip traces in this particular grain. And then we can expand it, not looking at only at that one area, but we can scan large areas and then perform the dislocation analysis. Now, from this map, we can calculate the geometrically necessary dislocations as well. And again, traditionally with geometrically necessary dislocation processing, you have to apply quite a bit of orientation filtering. But by re-indexing the real patterns with spherical indexing, you improve the angular resolution, and that will then really improve your G&D analysis without having to apply as much orientation smoothing. This very nice paper by Gregory Sparks really goes into quite some detail in terms of the parameters of the spherical indexing and the effects of pattern centering have on doing dislocation analysis on deformed structures. What you can also do is to take that orientation map and then apply this sort of adaptive domain misorientation analysis. And basically what it does, it takes a kernel average misorientation, but using a large number of nearest neighbors. And what it will give you is the sub-grain structure. So you can see that those areas in the sample that are very similar orientation, they will outline and it will identify these sub-grain structures quite nicely. Now, again, with this analysis, usually with normal EBSD maps, you have to apply lots of orientation filtering, and by re-indexing the patterns, you can get away with using much less of that filtering to determine the subgrains in the sample. The next example, it's from my PhD study where I worked in the oil and gas industry, and we looked at diamond drill bits, very good for drilling rock. But if you want to do electron microscopy on it, it's quite difficult to prepare a good surface. And EBSD analysis are very, very sensitive to the surface preparation. So we have these micron-sized diamond grains that's in the order of 20 microns, and then there's also smaller diamond grains that's mixed in to improve the packing density. And when we do the Hough-based analysis, you can see that there are a lot of sort of misorientations or misidentified orientations here in the map, and this makes grain size analysis or orientation analysis really, really difficult on this material. Now, we identify the indexing success rate as all those pixels that's belonging to at least a grain that have a 5-degree misorientation, and that's at least 4 pixels in size and at least over 2 rows. So there's different ways of defining indexing success, but we in this presentation we will use this definition. And if you apply that definition, you would see from the Hough-based indexing we only get an indexing success rate of 58%. So only 58% of the pixels are belonging to a real grain, and all the other ones are single pixel misorientated grains. You can improve the analysis by averaging the patterns and then performing Hough indexing. So in the OIM matrix software, you can re-index the patterns after averaging them, and that improves the indexing success rate to 84%. And then if you apply spherical indexing, that indexing success rate jumps all the way to 99%. And that's really important if you want to analyze these sort of smaller grains that's sitting in between these larger grains. And with that, we also get an increase in the angular resolution. This particular sample has been mechanically polished with a diamond impregnated resin wheel. And to do misorientation analysis, we still get not as good results as possible. And we can potentially improve this by employing iron polishing as well. So by improving the surface quality of the sample using iron polishing, that in combination with spherical indexing will then allow us to do the deformation analysis on this polycrystalline diamond sample. The next material that we looked at is from our welding institute at Ohio State, and in this project they welded a nickel filler material, which is a FCC material, onto a substrate of iron, which is BCC. And during this high temperature process, the molten nickel will diffuse into the iron, and then it would, at high temperature, it will form austenite in the iron. And upon cooling, this austenite will then convert to martensite, and it will form a very fine grains, fine lath structure right here at the interface between the filler material and the solid substrate. And in this project, they are very interested in analyzing the orientation relationships. Now, if you do traditional Hough-based indexing with all these misindexed pixels, it's very difficult to do reliable orientation analysis. By performing spherical analysis on the saved patterns and applying pattern averaging, we can really improve the analysis. If we then overlay it with the image quality, we can start to see that the martensitic laths for that's adjacent to this particular nickel grain has got a certain color, and the martensitic laths adjacent to this particular nickel grain has got a certain color. And in the OIM analysis software, you can also do prior parent grain reconstruction. So after re-indexing, you can then do this parent grain reconstruction, where you choose a idealistic orientation relationship, and then reconstruct from these martensitic laths the high temperature phase. And then this is what we see here on the screen. And then you can see that for this particular martensitic phase, when you reconstruct it into its prior austenite grain, it is epitaxial to the nickel grain that's solidified on top of it. And with this particular martensitic phase, it's epitaxial with this particular nickel grain. We're also interested in studying now the orientations between the martensitic lath and the actual substrate, but this is all made possible if you re-index it, and then we can also do this prior grain reconstruction. Now, this assumes an idealistic orientation relationship, and it can be a little bit sensitive to the parameters that you choose here, but it's all built into the software. And if your orientation relationship for your variants are very, very close to the theoretical one, it usually works quite well. Now, to improve the spatial resolution of your EBSD analysis, instead of analyzing a bulk sample where you have the electron beam penetrating into the material and forming an interaction volume on the order of 50 to 100 nanometers in size, to improve the spatial resolution, what you can do is to also analyze thin foils or thin samples in the scanning electron microscope. So instead of taking a bulk sample, tilting it to 70 degrees, we take a very thin specimen that you would prepare for transmission electron microscopy, and then by using the electron beam to go through the sample, we can get the same Kikuchi band information that we can analyze in the same way. And the consequence of that is that your spatial resolution improves by a factor of 10. So instead of having typical spatial resolutions for EBSD between 50 and 100 nanometers, for transmission Kikuchi diffraction, you'll regularly be able to get spatial resolutions in the order of 10 to 20 nanometers comfortably. And then I'll also show an example where we tried step sizes of 5 nanometers. And in this case, we analyzed a titanium alloy sample with a very, very fine microstructure. We used a step size of 20 nanometers, and we tilted the sample to an angle of -20 degrees relative to the horizontal. And then just doing normal EBSD analysis where we save all the patterns, we can then do re-indexing. So for traditional Hough-based indexing, there's a lot of overlapping patterns, and also the patterns are sometimes a little bit noisy. And then the other issue with TKD sometimes is the background subtraction that can be quite tricky. So for traditional Hough-based indexing for this particular sample, we got an indexing success rate of only 20%. Averaging the patterns to increase the signal to noise, that increases the indexing to about 56%. And then if we apply spherical indexing, that's much less sensitive to overlapping patterns, we can improve the indexing success rate up to 93%. In the following example, we looked at a nickel superalloy, and we focused in on one particular grain. And in this case, we were interested in mapping out the subgrain structure, or when you age the material, you form this sort of subgrain structures that got very slight orientation differences. And the focus of this particular study was to, are we able to map out these very small, low angle grain boundaries? The subgrains can be quite small as well, so we used a thin foil. So not only, so then we used the TKD analysis to get a high spatial resolution, and then by performing spherical indexing, we can improve the angular resolution to get high angular resolution as well. So by combining the TKD with the re-indexing, we can get both high spatial resolution and high angular resolution. And then we can very nicely map out these low angle grain boundaries for this particular nickel superalloy. The next example is also transmission Kikuchi diffraction. And here we looked at a transparent conductive oxide, and that's used in a solar cell application. And for this particular project, what they do, normally these layers are deposited onto a silicon substrate using a high vacuum sputtering technique. And for this project, they evaluated a high throughput atmospheric pressure spray technique to make this conductive oxide. But what they found is that there's sometimes there's a high contact resistance between these layers when you use this spray technique. And so we performed electron microscopy to really understand what's happening between these different layers. So we have a single crystal silicon, and then they first grow two polycrystalline silicon layers. That's got a very small grain size, so this scale here is 50 nanometers. And then on top of that, we have a zinc oxide, a zinc indium oxide, conductive oxide that's grown on top of it. And then on top of these ones, you have different layers of capping layers of titanium, palladium, and silver. So this is a bright field TM image, just show you a cross section of the different layers. And then here we have the that's cut off at the bottom. We have the large single crystal silicon. Then we have this polycrystalline layer of silicon, and then we have the zinc oxide polycrystalline layer that's grown on top of this. And then when you perform TKD analysis using a step size of 5 nanometers, with normal Hough-based indexing, we almost get very poor indexing success, and it's only really the single crystalline substrate that's indexing well. But then by performing spherical indexing, we can then map out these very small crystals in the sample reliably to determine the texturing, or to determine the texturing that might be present in this particular conductive oxide layer. So back to a bulk analysis. So a lot of my research involves analysis of power plant steels, and these power plant steels have got very small secondary phases, precipitates in them, that really strengthen the creep strength of the material. And these materials need to operate for 20, 30 years in service, but over time, these precipitates evolve and they change into different phases, and they also grow in size. And the objective of our study was to quantify how these precipitates evolve over time. So we're looking at high throughput techniques to map out these very tiny phases. And we try to analyze it with EBSD, but there's two issues. Sometimes these precipitates are really small, so it's very difficult to index the precipitates, because you're collecting information not only from the precipitate but also from the surrounding ion matrix. And then for this particular material grade, we ran into this issue where you have iron grains that have very similar positional bands compared to the M23C6 precipitate. And when you try and do Hough-based indexing, it really confuses the two phases. So what we do is we apply secondary electron imaging using the in-column detector, and we can map out different phases and distinguish them according to their contrast. So here we have these green precipitates marked with green dots, and they have this gray color. Then we have these darker precipitates, and then also we have these brighter outline precipitates. Now, to determine the crystallographic information, usually you have to cut out a TEM foil using a focused ion beam and then do the analysis in the transmission electron microscope to determine the phase. And what we're trying to do here is to use EBSD analysis to at least identify these crystal structures or map them to what we think they are. And when you do it with spherical indexing, you can see that the ambiguity between the precipitate and the matrix is completely resolved. So we can reliably index the BCC iron grain. And then for these precipitates, we see that these dark precipitate maps out as the Z phase or the Z phase. And then these brighter ones marked with the yellow is the Lavis phase. And then the green ones are the M23s. Using slightly lower beam conditions, so we drop down the accelerating voltage to 10 kV to minimize the interaction volume. We drop down the step size, and then with spherical indexing and non-local pattern averaging, we can then map out these very small precipitates in the steel by this reanalysis. Now we can use this secondary imaging over large areas to map out these crystallographic phases, and then quantitatively determine the proportion of the secondary phases, which then can go into prediction models that would be linked to the mechanical properties. An alternative way to improve the spatial resolution of the EBSD analysis, we also have this experimental EBSD camera that operates in a flat geometry. So in this case, we have our sample is at 0 degree tilt, and then the EBSD camera slides, or the detector slides in like a backscatter detector, and it sits above the sample. And this detector consists of 4 time-pix detector chips, and they arranged in this configuration. So right in the center, there's a hole in the detector where the electron beam can go through the detector to hit the sample. And then the diffraction information is then collected at 0 degree tilt. Now, the advantage of this analysis is that the beam penetrates straight through the sample in normal incidence, and that the footprint of the interaction volume is then in the lateral resolution is much better. If you want to read more about the detector and also the improvement in spatial resolution for this particular detector, you can find the details in this particular paper. So that's the benefit, but the downside is that the backscatter yield is a factor of 10 less. So there's a reason why we perform EBSD analysis at 70 degree tilt, is because you get a lot of signal. So if you place the sample at 0 degree tilt, then you get a lot less signal. So the patterns are quite noisy, and that makes it sometimes very difficult to analyze. So yes, you get an improvement in spatial resolution, but these patterns can be quite tricky to reliably index. And by saving all these patterns and then re-indexing with spherical indexing, which is much more sensitive to noisy patterns, you can then improve the analysis. So getting both good spatial resolution and also improve the angular resolution. So we applied it directly on the power plant steel sample. So here's the secondary electron image showing you the different precipitate types, the contrast. And then if you map out the phases, you can see that for a step size of 30 nanometers, we can then map out the crystallographic phases reliably that correspond to these different image intensities. And the other advantage is that you don't really have to tilt the sample. So it's all flat. You just retract this detector and then you can do imaging with all the other analysis without moving the sample and losing the actual place where you want to do the imaging. What we can also do is to do transmission analysis. So we can take a very thin sample. In this case, it's again these steel precipitates in this power plant steel, and we prepared a jet polished, electropolished foil sample with a hole in the center, and then right around the hole, the sample is electron transparent, so it's thin enough that electrons can actually travel through the sample. But you end up with this sort of a wedge-shaped material where around the hole, the sample is very, very thin. And then as you move away from the hole in the sample, then the material gets progressively thicker. If we use this stem detector that we place underneath the thin foil, we can image the structure, and this is very similar to stem analysis in the TM, and we can see that these dark features here is all the precipitates. We can see the subgrain boundaries that outline quite nicely, and in addition to the subgrain boundaries, we can also see the free dislocations. So these are dislocations that might not necessarily cause a rotation of the crystal, and they will be invisible for EBSD analysis. So by combining this transmission mode with orientation analysis, that will allow us to see the total dislocation density in this particular material. Now for TKD analysis on a material where the thickness varies quite a bit can be quite challenging. And in the OIM software, there's a very nice post-processing of the patterns where you can perform advanced background subtraction. And for TKD patterns, what you want to maybe avoid is to do a static background correction, because the background will be different depending on the thickness of the foil. And in this case, we apply a dynamic background division instead of subtraction, and that works quite well. And then just a histogram, adaptive histogram equalization to map out, and then you can get very nice quality patterns with high contrast that will really also help to improve the indexing success. If we then map out the that same area that I showed the image of, we can then re-index those patterns, because they with the spherical re-indexing, that would really improve the indexing success rate and the angular accuracy and also the spatial resolution. So the top left shows the inverse pole figure of showing you the different orientations within the grain. On the right here, for that same TKD map that we performed, we did the kernel average misorientation, and we stretched the angular resolution all the way only from 0 to 1 degree, and you can get these sort of low angle grain boundaries that maps out quite clearly. And then for this material, there's only 2 phases. So it's the iron, which is marked as red, and then the M23C6 precipitates, and we can map out the crystallographic phases. For this particular scan, we also included EDS analysis. So using thin foils, we can get improve the angle, the spatial resolution of your chemical analysis as well. So we can clearly map out the composition of the features by looking at a thin foil. And then lastly, using this transmission stem detector, we can then map out over that same area, we can see the position of the precipitates, we can see the subgrain boundaries, and we can also see these smaller dislocations that might not necessarily cause a rotation of the crystal, and therefore it will be invisible for EBSD analysis. So by combining this STEM image with the orientation information, we can characterize all the dislocations that's in this particular material. So using this sort of multimodal correlative analysis in the SEM, you can really characterize all the features down to a nanometer scale. So in summary, spherical indexing as implemented in the OIM Matrix software has got all the advantages of dictionary indexing, has over half indexing, but it runs much faster because you only have one pattern to compare against, your experimental patterns. So that when you apply it practically, you don't really have to think about all the equations or anything. It's all built in a user-friendly environment, and then you have all these additional tools that you can filter the patterns, you average the patterns, you can subtract the background, you can do the pattern center optimization, all within one program to then map out to improve the analysis. And then if you take an image of a SEM image or a transmission STEM image, you can import that image into the software and then register that image so that it lines up with the orientation information to then plot these different kinds of information over each other. So that really facilitates the correlative techniques that you can get from these modern instruments. So just another plug for the SEM course that we have at CMAS. We have early registration open until March 11, 2025. And when I joined CMAS, I looked at these course materials just before, and even though I've worked with EBSD and EDS before, having these lectures given by the industry experts, even though I've worked with these techniques before, there was significant amount of learning that I could still get from these videos. And then all the techniques that I showed in this presentation are available at CMAS. So then part of this course you get to work hands-on, and I think on day 3 we have some time left over, and if you bring your own samples, part of this course we can make time and we can perform analysis of your own materials. So I could strongly encourage just following the link and then checking out the details for this particular course. Over and above the course, if you're interested in applying some of these techniques that you've seen in this presentation to your own material, I've shown a lot of examples of steels, but we apply it on superalloys, titanium alloys, and also aluminum. So that's another, I think, material system that can really benefit from these correlative type techniques that we have available at CMAS. And then SEMs is only one very tiny part of CMAS. We have a comprehensive suite of instruments, very advanced transmission electron microscopes, and also cryo transmission electron microscopes that if you're interested in that analysis, you can just contact cmas@osu.edu, or you can find more information on the website. So that concludes my presentation. So I open up the floor for questions.
Hi, Johan. Thank you very much for that presentation. It was wonderful. We have a few questions, if you don't mind asking a few, and if we don't get to all of them, we'll answer those afterwards. The first question is, how did you select the 127 bandwidth for the spherical indexing? Is that a parameter that you've experimented with?
Yeah, so based on literature and also experiments, if I can go all the way back to this slide, yeah. So if you take your raw pattern, that is all the information that's contained within the material. And then using this bandwidth of 127, you can see that it's faithfully represented. And then if you look at the grid spacing here, the discretization is about 1.4 degrees, which is similar to dictionary indexing. So if you perform refinements on something that's 1.4 degrees, it usually converges quite nicely. And then also the time. So by using higher and higher bandwidth, you really decreasing the indexing or re-indexing speed. So 127 is sort of an experimental value that works quite well for the samples that I'm. If you really want to push the limits of angular resolution, then you might want to consider using the higher bandwidths. Or if you have phases that are very similar, and you're interested in the very fine details to distinguish between those different phases, then you might want to consider using a higher bandwidth.
Perfect, thanks. Okay, another question. It says you showed MPAR worked well for your TKD results, but you'd mentioned the MPAR can also blur results. Is there a step size recommendation to avoid the blurring you mentioned?
Yes, so usually for the TKD patterns, NPAR runs a little bit quicker because it doesn't have to do the similarity comparison. And for this particular example, we really pushed the spatial resolution down to 5 nanometers. So then if you perform NPAR, you're going to blur out the information, and then it's going to be difficult to resolve these very small crystallites. So in this case, we have very noisy patterns and a very small step size. And in this case, we use this non-local pattern averaging, and that will only average the patterns if they belong or if they're similar to that particular pixel. So NPAR usually for like 20 nanometer step sizes and above, NPAR works quite fine for TKD. But if you go below that, you might want to consider using the non-local pattern averaging because it preserves the spatial resolution.
Have you tried fib serial sectioning in EBSD, 3D EBSD with spherical indexing?
So I haven't done that analysis personally, but I know Will Lenthe from Carnegie Mellon, he's got a paper out on doing exactly that. So the one thing is you have to save all those patterns for each EBSD map for each slice, and it becomes just a ginormous data set. So I know there's developments now where if you really optimize the patterns, you can do them on the fly, and I'm sure EDAX can comment on inline EBSD indexing, the state of that development, because it is matching almost the speeds of Hough indexing currently. So I know that's something probably in the future where going directly from the patterns from the detector, indexing it with spherical directly, skipping the Hough indexing step directly. So that's probably where it's heading in the future. Then you don't have to save all these patterns and work with these ginormous data sets.
Yeah, I'd concur with that. Do you have any experience of using this spherical indexing with materials that have pseudosymmetry?
So no. So very interesting. Will Lenthe has got a paper out from Carnegie Mellon where they, oops, let me just get to that slide. where they analyzed pseudosymmetry. Sorry, let me just get to that. Yeah, so interesting fact, if you take this master pattern and instead of doing the cross correlation with an experimental pattern, you do the cross correlation with the master pattern itself, you can then identify whether or not a particular crystal is going to be susceptible to pseudosymmetry. So pseudosymmetry is when you have, in the same crystal, you have multiple orientations that look the same. So then by performing a autocorrelation on this master pattern, you can identify which materials. And then in that paper, they describe how to address pseudosymmetry issues using the spherical indexing. But yeah, so I used it for phase discrimination, but pseudosymmetry issues I think can be addressed by the spherical indexing.
And then this one is a two-parter. It says, hi, Johan, did you perform the adaptive dam analysis on both Hough indexing and spherical indexing to form 316 steel? And then it says, if yes, were there significant improvements in resolving the GND? And essentially, I guess, yeah.
Yeah, so I haven't made that comparison. So in this case, I think if you do apply it with just the normal Hough indexing, you get quite a reasonable result. But in that process, you have to really filter the orientations quite significantly. And each additional processing step that you perform, where you would smooth out orientations, that is removing gradients or that might be present in the sample, and that's related to the deformation. But I haven't done a systematic study of that yet, so that's still work in progress. The one I show here on the screen, that was performed after spherical re-indexing, and then I performed the adaptive analysis. As far as I know, this is not implemented, and Matt can correct me, in OIM Matrix, so that was done using MTEX.
Okay, yeah, that's correct. And then one last question we have is, when we'll use 45 degree in the EBSD technique? I'm not sure exactly how that goes, if that's relative to your TKD slide or.
No, that's fine. Let me just get to one of the images now. So 45, okay, this is also an TKD slide, but usually we tilt it at 70 degrees. And that is to maximize the backscatter yield. So at 70 degrees, they found that's the optimum. If you tilt it 45, you'll get less signal. Also, what you get very interestingly is that the beam will penetrate a little bit deeper into the sample, and then what you get at 45 or at 52 at least, you get band inversion. So these bands here that form at the bottom, they're a little bit darker than the bands on top, and that can actually, make if you do spherical re-indexing, that can make it quite challenging. And the reason is that you have the beam traveling through a bigger portion of the crystal, and then you get a dynamical anomalous absorption effects that will change the band contrast. So 45 degree will reduce the signal, and it might result in band contrast inversions that will make your EBSD analysis very, very challenging. So the flat analysis that results in increase or improvement in the spatial resolution, but at the cost of decreased signal.
Perfect. Well, thank you, Johan, for the wonderful webinar and answering these questions, and thank you everyone for attending. And I Have a good rest of your day, wherever you are.
Okay, thank you very much for your attention.